Welcome to the final part of the acids and bases lecture. In this section, we will look at salts and buffer solutions. Which of the following statements about salts is incorrect? If you had answered C, you are right. Not all salts have a neutral pH. The salts of weak acids or weak bases are usually not neutral. Salts are ionic compounds formed in an acid-base reaction. They consist of a positive and a negative ion. The positive ion could be a metal or polyatomic ion, and the negative ion could be a non-metal or polyatomic ion. However, if the ionic compound has a hydroxide ion, OH- ion, it is a base instead of a salt. Can you name the following salts? This should be very familiar to you. You would name the cation first, followed by the anion. These are the answers. Now let's look at buffer solutions. Buffer solutions are solutions whose pH remains almost unchanged even if a little bit of acid or a little bit of alkali is added to it. This is because buffers have the ability to remove most of the extra acid or alkali that's added to it. Buffers are widely used in the lab when it is important to maintain a constant pH. For example, cells need to be kept in a buffer to maintain the proper pH for their enzymes to function. The rate of biochemical reactions involving enzymes is dependent on pH. Electrophoresis, a technique used to separate proteins, also requires the use of buffers. Buffers can be made by mixing a weak acid with a salt of the weak acid. For example, by mixing ethanoic acid and its salt, sodium ethanoate. Buffers can also be made by mixing a weak base with a salt of the weak base. For example, by mixing ammonia and its salt, ammonium chloride. So, how does a buffer work? Let's use the ethanoate buffer as an example. The ethanoate buffer contains a mixture of ethanoic acid, CH3COOH, and sodium ethanoate. Ethanoic acid, CH3COOH, is a weak acid and exists mostly in the undissociated form. Sodium ethanoate, CH3COONA, would dissociate in water to form Na+ and CH3COO-. I hope you recognize that CH3COO- is actually the conjugate base of CH3COOH. If a little bit of base is added to this buffer solution, ethanoic acid in the buffer will react with the base to neutralize it. Notice that this reaction has a forward arrow over here. For acid-base reactions, as long as a strong acid or strong base is involved, the reaction is irreversible. So if a strong base like OH- is added, the reaction is irreversible. If a little bit of acid is added to the buffer solution, the ethanoate ion CH3COO- will react with the acid to neutralize it. Again, notice that the reaction has a forward arrow. If a strong acid is added, the reaction is irreversible. Let's try a calculation question involving a buffer solution. Calculate the pH of a buffer solution consisting of 1.0 molar CH3COOH and 1.0 molar CH3COONA. The Ka value is also provided. Let's start by writing the acid dissociation reaction of CH3COOH. Now, take a look at the components of the buffer. Can you identify the conjugate acid-base pair in the buffer? CH3COOH is a weak acid, and CH3COONA would dissociate to give CH3COO-, which is the conjugate base of CH3COOH. Now let's use the Henderson-Hasselbalch equation that was introduced in part 3 of the acid-base lecture. pH equals to pKa plus log conjugate base over weak acid. Putting the values into the equation, we can calculate the pH of the buffer solution, which is 4.74. Now, what happens if 0.1 mole of HCl is added to 1 liter of the buffer solution? Can you identify which component in the buffer would react with HCl to neutralize it? CH3COO- is a base, so it can react with the added acid. Let's write the equation of the reaction that occurs. I've written a simplified equation using H plus to represent the acid. When this reaction occurs, it causes a change in the amount of CH3COOH and CH3COO- present in the buffer solution. We will need to calculate the new amounts of CH3COOH and CH3COO- in the buffer. But first, let's start by calculating the initial number of moles of CH3COO-, H+, and CH3COOH. Press pause to do your calculations, then press play to check your answers. Based on the information in the question, the concentrations of CH3COO- and CH3COOH are 1 molar. The volume of buffer solution is 1 liter. So we are starting with 1 mole each of CH3COO- and CH3COOH. The question also states that 0.1 mole of HCl is added to the buffer. Now let's calculate how many moles of CH3COO- and CH3COOH are present after the reaction with HCl. Press pause to do your calculations, then press play to check your answer. Since the stoichiometric ratio of CH3COO- to H+ is 1:1, 0.1 moles of CH3COO- would react with 0.1 mole of H+. So the remaining number of moles is 1 minus 0.1, which is 0.9 moles. The stoichiometric ratio of CH3COOH to H+ is also 1:1. So 0.1 mole of CH3COOH is formed. The total number of moles of CH3COOH becomes 1 plus 0.1 equals to 1.1 moles. Now let's put our values into the Henderson-Hasselbalch equation to calculate the pH of the buffer solution. You should get a pH value of 4.66. Finally, let's look at the buffer system in our blood. Blood contains a buffer of carbonic acid H2CO3 and bicarbonate HCO3- in order to maintain the pH of blood close to pH 7.4. This buffer helps to neutralize any excess acid, for example, lactic acid that's produced during anaerobic exercise. H2CO3 is a weak acid, and HCO3- is its conjugate base. Any excess acid is removed through neutralization by HCO3- to form carbonic acid. Carbonic acid is unstable and breaks down to form carbon dioxide and water. We've reached the end of the acids and bases lecture. After this lecture, you need to be able to explain what is an acid or a base according to the Bronsted-Lowry acid-base theory. You need to be able to identify a conjugate acid or base for a weak base or acid. You need to explain the difference between strong and weak acids. You also need to know how to perform calculations related to pH, Ka, Kb, pKa, and pKb. As for buffers, you will need to know how to explain what buffers are, and to perform calculations related to the pH of buffers, using the Henderson-Hasselbalch equation.